Dear viewers, dear ladies and gentlemen, we are very happy to welcome Dr. Oladele Ogunseitan, and he will tell more about the research that he is doing in his research laboratory. Dr. Oladele, could you please tell us more about the research projects you have and the research goal and the mission of your research laboratory?
Thank you, Ina. I am trained as a microbiologist and also as an environmental health scientist. And my research has taken two directions that are complementary. My early work in microbiology was really looking at ways we can use genetically engineered organisms to clean up polluted environments. But I was more interested in the risk assessment of such genetically engineered organisms. And so I looked at the transduction of genes from one bacterial cell to another in natural environments. And we used antibiotic resistance markers to track those genes. Little did I know at the time that antibiotic resistance will become a major global health problem. And I still work on that research today. I have many students who are interested in that topic. It's probably the greatest threat to public health that we have seen in the last 50 years, because the gains of treating infectious diseases is we're losing track. The second line of research has to do with some of the outcomes of the work that I've done also in environmental microbiology and diversity. It turns out that many antibiotic resistance genes are also on plasmids that encode genes for toxic chemical degradation. You can think of toxic chemicals as metals like lead, mercury, and that led me to thinking about products that introduce these toxic chemicals into the environment. And I started collaborating with material scientists who are interested in electronic products that have lead, mercury, cadmium, nickel. And I have a big part of my lab that's focused on trying to get electronic products to become greener using safer, less toxic materials, because at the beginning of their life cycle, throughout their use to the end of their life cycle, they should pose minimal or no threats to human health and environmental quality.
Thank you so much for this. These are two very innovative lines of the research. What is the end goal of your research laboratory? What ideally would you like to achieve with your research in the future?
So for the electronic waste project, that is a very clear goal. The World Health Organization documented last year that 18 million children and about 13 million women work to get small amounts of gold and silver and copper from electronic waste. And in so doing, they are poisoning themselves because of the lead, mercury, nickel, cadmium, and brominated flame retardants. My goal is to remake the way we manufacture electronic products so that they no longer pose these kinds of threats to women and children. But it begins more with how we recover minerals from the planet. Something like cobalt, for example, that we now mine from the Democratic Republic of Congo. Again, sometimes children work in those mines and their health is compromised. We shouldn't have to go to raw minerals anymore for such metals. We can recycle electronics in a way that allows us to get as much cobalt as we need. You can name many different minerals. Lithium, for example, is the same problem. So if I get to the point where the big electronics manufacturers, Apple, Dell, uh, Microsoft, Google, Samsung, uh, really get to the point where they're no longer um, uh, putting toxic chemicals into their products and recycling what they need rather than mining the earth, then I would have been successful. The second, of course, is that we no longer need to worry about antibiotic resistant infections, right? But to me, that's a very tricky goal because bacteria are always evolving, and it's a very challenging longer term goal. But the electronic waste goal, I think, is achievable with very specific sub goals that we scientists collaborating with manufacturers and consumers playing their part. We need to have this transdisciplinary way of doing the research.
Sure. Material science somehow show to be always easier than the biology because biology is always evolving. It is very difficult to catch. You need to invent new strategies how to intervene. At what stage your project with the second project with the metal parts is currently located? Do you have any agreements with the big companies? Is this still in the R&D phase, or you already moved more into commercial?
We're not yet in R&D. I do have a project funded by Microsoft, and they're interested in biologically based materials for printed circuit boards. And that is a very, very promising project. There are already some prototypes. There are companies that are manufacturing such products, but I don't think they're at scale yet. So on my campus, we have a group of us that meet regularly. We call it Solutions at Scale. So there are many, many prototypes. We work with a company that's actually funding my institute. I'm co-director of the World Institute for Sustainable Development of Materials. And the person who gave funding for that institute, Dr. Johnny Lincoln, really works on using flax, which is linen materials, to create printed circuit board baseboards. There are still challenges that we have to walk through in terms of moisture retention. All right, but again, there are proprietary things that step by step as you go toward commercialization, you have to be aware of. But the driving goal is that these kinds of materials will not use the toxic flame retardants, and they will be easy to recycle. There's a company in England called Java Board that's already making, they have a website showing that you could dissolve the printed circuit board in water and get all the components back and make it easy to recycle. So you're right. The material science aspect is pretty straightforward, commercializable, and there are prototypes, but right now you will not find such printed circuit boards in your phone or the computer. The biology, yeah, go ahead.
Sure. What are the challenges to scale here this technology? What are your major bottlenecks?
Electronic products have to meet many criteria for performance, right? So we expect the best speed, the best stability. There's a drop test. If you drop your phone from a certain height, you should be able to pick it up. But there's also, so that's one of the challenges, is to make sure that if you use the biologically based material, that it performs exactly, if not better, than the current materials. There is the economics, how much people are willing to afford. We're, interested in using biologically based materials, but there are already uses for those things. So if we say flax, We have to think about the fabric industry. We have to think potentially about the food industry competing for those resources so that the cost of getting food is not pushed too high that people will not be able to afford them, but also that we have enough to make products for everybody at a reasonable cost. And there is also the performance, I'd say, is probably the biggest challenge, particularly the longevity, right? So if this is iPhone 7 that I've been using for quite some time. Many of my colleagues have moved on to iPhone 14. And so the longevity is good. It's not exactly good for the company because they are not making the profit from me buying a new phone. So we have to work with manufacturers to think also about how to scale so that they see profit in transitioning the platform from petrochemically based materials to maybe biologically based, less toxic materials. But from my perspective, the biggest challenge right now is the moisture holding capacity, which affects performance and things like that. But there is a lot of possibilities, but we can't, until we peer review and publish them, we can't advertise them.
Sure. Talking about your first line of research, finding the antibacterial resistance, how much progress do you have at least on this field? Do you have any inventions which are already based in the clinics?
Not yet. And I should say that very early on in the 1980s and 90s, when I was working on Pseudomonas aeruginosa and the bacterial viruses that infected, aeruginosa is a complicating bacterium in cystic fibrosis, for example. It produces materials that make it very difficult for antibiotics to attack it. And when they become even resistant to the frontline antibiotics, it could be a problem. Phage therapy is promising. I have a colleague at UC San Diego who's investing a lot of energy and time and money in phage therapy. I think there is promise there. But I also recall that it was a very popular topic in Eastern Europe and Russia many, many years ago. But because the chemical antibiotics were so successful, we kind of abandoned the phage therapy approach. I think there is a possibility there, but as you said, bacteria evolve, phage evolve, and so it's a ongoing battle. So you have to keep catching up, and that's one of the big differences because the phage can be engineered, in my view, to play catch up more quickly than the bacteria can evolve. And so we have to really think about creative ways to get around the tit for tat fights that bacteria and phage engage in. A lot of the work that I've done on antibiotic resistance is also mostly about understanding the misuse of antibiotics in agriculture and in hospitals. So part of it is the community engagement and education of the physicians. Because while we're looking for the best new frontiers of killing pathogens, we also have to know that it takes a lot of time and money to go from the lab to new drugs. I mean, there's a good reason the big pharmaceutical industries have not yet announced, the silver bullet to kill a lot of bacterial pathogens because it takes time and money to get to that point. But we have to move that industry in the right direction by showing the promise of new technologies and new ways of doing things. But I don't have anything yet that could be commercialized in that perspective.
Yeah. There is a company in Germany called Invitris. It was founded recently, maybe around 2 years ago, and they are focusing on finding the resistance with the help of the bacteriophages. Right. Of course, it is still in the R&D phase. It is very early to say anything, but there are such companies rising.
Yes.
Talking about the scientific side of your research, which strategies, which lines of the research do you pursue in order to address the topic of the bacterial resistance? It is more on molecular levels, on the level of fighting the pathways, the wiring, or this is more on developing some small molecules as a chemicals or phage therapy. Could you share more information here?
Yeah, I just returned from Europe on Sunday, and I visited the University of Oxford, and there is a museum there with the original flask that Fleming grew the fungus, right? And I think we now know a lot more about the molecular biology of antibiotic production, antibiotic sensitivity. But there is also still a field work that still needs to be done. I wrote a book on microbial diversity, and I know out there in nature, in soils, in sediments, in water, we probably have what I would consider a magic bullet. So I'm very interested in the ecological approach to finding new antibiotics that will work. So there are people combing, the marshes and testing, just like, and some of it is accidental, just like Fleming's and Florian Chain and their experiments. But, I think the way that we're worried now about the pathogens that may come back, we know a lot more about them in terms of the molecular level, that we need to understand how best to sidetrack their natural defenses, including resistance to bacteriophage. So there are certain biochemicals, bacteriocins, that are derivatives of bacterial viruses that I think are more promising from the lab perspective, based on what we already know, that probably is being engineered. And I don't know what strategy the company you refer to in Germany is using, but it's kind of like vaccines, right? You can, there are people trying to develop a vaccine, a universal vaccine, right? That if the reason every season the flu vaccine, we have to reinvent it and give it to people again, is because the flu virus is very smart. It keeps dodging the bullet. But there is a hope for a universal vaccine if we can find the right target. And I think for many of the frontline pathogens, bacterial pathogens, doing the right molecular biology to find that vulnerable point in their physiology and targeting that is really critical. I'm not at the forefront of that kind of research anymore, but I know that there are people who will probably beat us to the punch.
Sure. So it looks like your lab is very diverse in terms of the background of those people required to do the research, to perform these two lines of the front research. To those people who are viewing us, those who are wanting to join your research laboratory, whether these are bachelor, master, PhD students, or whether these are already more on the senior level of the scientist and the postdoctorant, what would you say to them? What shall they consider? What can they expect when they would like to join your research laboratory?
Yes, the talents are, some are more chemistry oriented, right? And some are more the biology oriented. Actually, I have a third group that are more, community engagement. But for the electronic waste, I've worked primarily with more senior. I have collaborators in material science here in the United States, in China, in terms of looking at toxic pollution. We've done work with people in different parts of the world. And they come to my lab and they can lead projects in different directions. And that is exciting for students, because from the undergraduate to the masters in public health, to PhD and junior faculty, visiting scholars. They have a network that can help their career as they graduate from my research group. For the antibiotic resistance work, most of them are interested in public health. The biology students, public health science students, and I've had PhD students, and not as many senior faculty, junior faculty who have come, although there are very strong PhD students who I hope will become postdocs and start their own line of research. I think a very strong understanding of molecular biology is essential. And there are students who are inclined to work in that sort of bench scale. But I'm also interested in finding people who can bridge the molecular biology with the ecology, who can go and sample water systems and wastewater and bring them to the lab and discover new ways of thinking around antibiotics. So if a student has the sort of dirty soil, being out in the field, but they can also come back to the lab and put on their lab coat and do really good molecular biology. In my days, we call that the molecular ecologists, and that will be a very good student for my group.
Sure, thank you so much. In terms of the message, the patients, those who are concerned and their families, I think we have spoken enough about the public health and what we do for that. Let's focus on the group of the investors, those that are VCs and the business angels. What would you say to them on your latest developments and where the field can go in the future for both lines of your research?
Yeah, for the electronics, that's where a lot of money is. It's money. We have a training grant now with colleagues at UCLA it's funded by National Institute of Environmental Health Sciences. It's about occupational health. There's big money there. There's a lot of investment, but we have to find the investors want the right thing to invest in, right? I think there is a sense that a disruption is coming in this industry because of not only because of the negative aspects of putting pollution out in the environment. A lot of these companies are trying to lower their environmental footprint, but the investors need to identify that transformational discovery. Bio-based electronics, I would put my money there. I think there are investors who should start thinking about that. So it needs a little bit of a push at the research level, but once we find the right mix of things that is performing well, the scale up will be quick, and I think the industry will be disrupted. For the antibiotic resistance project, there is also an opportunity for disruption. On good days, I think it will come from phage therapy, but that topic has been around for so long that I'm beginning to worry if it's truly capable of disrupting the current situation. So combinatorial chemistry and finding just doing things rapidly, using robotics to test a lot of chemicals might be a way to go. And I know there are some investors interested in that approach. I will still put my money in the molecular ecology that somebody from my lab may come up with a new antibiotic from the marshes somewhere. But we need to go wider than the current scope of work. So I think investors who are interested in biodiversity and biomining is what I call it. It would be a good opportunity.
Sure, thank you so much for this information. It is very interesting. Besides that, what we already spoken about, would you have something to add that is still of significant value, but we haven't spoken about it yet?
I think we covered most of what I think about on a day-to-day basis. When I have new students asking me, "Oh, I read this paper, I want to come work with you," I ask them about their long-term goals and their skills, and it takes patience, right? When I talk about these two lines of research, in my mind, they're still about toxic chemicals and how they interact with living systems and how we can do better. But the ultimate goal of commercializing a product should be secondary to a new student's mind. They should really just want to discover something, and if it becomes commercially viable, that's a good thing. Some students want to start with, they want to have a startup company and make money right away. And I said, well, you have to have something to sell. And, it takes diligence and late nights in the lab and in front of your computer. So, I still practice that, but one also needs to have a life. And because some of that creativity comes with talking to different people, collaborating widely, learning new topics from different fields. I value my ability to talk to people, from engineering to social sciences to biology to medicine. To me, that is growth, and that helps me, ground myself. That there's always more that I can learn than I already know. But different approaches for different people. For this one works for me.
Good. Thank you so much for this interview. It was a pleasure to have you.
Thank you, Ina. Appreciate it.